Hi guys, welcome back to lecture 2 of chapter 13. So we're going to go back and we're going to talk about stacks a little bit. So in the previous chapter we developed our own array-based version of a stack, and we also used java.util.stack, the class from the Java API. So the API's class is derived from vector, which has many non-stack capabilities. Vector is kind of like an array that that you don't have to worry about resizing, like it resizes itself automatically. So it's not the best example of inheritance because a stack isn't a vector, and a vector has a lot of things that a stack doesn't have. For example, you can remove things from the end of the bottom of a stack because you can remove things from the end of a vector or beginning of a vector. So there's lots of stuff that you can do that sort of violate the idea of being a stack, and sometimes those things are useful, to be honest. But, you know, it's a little bit iffy. Stack characteristics can also be found using the deck interface from the APIs. That's pronounced deck, in case you're curious. Not DQ. The linked list class implements the deck interface. So the deck stands for double-ended queue, which we're going to talk about later. But for now, we're going to use the stack characteristics of the deck to solve the problem of traversing a maze. So suppose we have a two-dimensional maze. It's represented as a grid of one path and one wall, and zero wall. And the goal is to traverse from the left corner to the bottom right with no diagonal moves allowed. All right, so we want to go from the left corner of this maze to the bottom right, and we can only walk on the ones, is the rule, right? And we can't go diagonally. So we want to find the path from, you know, the upper left corner to the bottom right with no diagonal moves. All right, so to do this, we're going to have to do backtracking, which backtracking means we're going to follow a path, we're going to find out that we took the wrong branch, and we're going to back up until the previous fork. So if you look at this maze, you know, you come here, step one, there's two ways we could go. We could either go right or we could go down, right? So let's say our rule says we always go right first. So we're going to go right, but that's the wrong way, right? So we're going to get here to this point and we're going to realize that we can't go right and we can't go down anymore. So we went the wrong way. And so we're going to have to backtrack to the previous branch, right? But think about it, there may be multiple branches involved here that we have to backtrack through. So what we're going to do is we're going to use the stack to store the branch location every time we branch. And that way we can backtrack to the last branch, search all of those, and then if we don't find anything, we keep backtracking, if that makes sense to you. All right, so we're going to have an object that represents the position in the maze that we're going to push onto the stack when we try a path. So if we encounter a dead end, the position is going to be popped and another path is going to be tried. So we'll change the integers in the maze grid to represent a tried but failed paths 2 and successful path 3. All right, so let's look at our code here. So we have some constants here that we're going to declare. Tried equals 2, path equals 3. We're going to have private int num rows, num columns. So that's going to be the size of our matrix. Our matrix. And then we're going to have private int. So this is our two-dimensional array called grid. So our maze, we're going to read this in from a file. We're going to look for number of rows, number of columns, and then our grid. So that's, if you look at our file format here, 913, number of rows, numbers of columns. Then we're going to allocate an array that size, and then we're going to go through and we're going to read in the integers from the grid, just the ones and the zeros. So this initial bit is going to let us allocate the array, the 2D array. Once we've allocated it, we're going to go in and fill it in with zeros and ones. Right? So here is our function to mark where we're going to try. We're going to try position int row, int column. We're going to have grid, row, and column, and that's going to be tried. Because we've tried that position, we're going to return a number of rows in the maze. That's just an accessor function. Return a number of columns in the maze. We're going to mark the path. So this is the valid path that we found so far. So this is going to determine if a specific location is valid. A valid location is one that's on the grid but not blocked and has not been tried. So we're going to have this Boolean valid position, int row. We're going to pass in these coordinates. It's going to start off as being false. If it's in the bounds of the matrix and it's not blocked and not tried, then it's a valid path, and we're going to return that. So toString is going to return a string representation of the matrix, basically just going to let us print it out. All right. So now we have our maze solver class, and this is the one that's actually going to solve. It's going to have a maze inside of it, a maze instance inside of it. We're going to create that in the constructor. So we're going to have this function called traverse, which returns a true or false. It's a Boolean. So what it's going to do, just reading the thing, it's going to attempt to traverse the maze using a stack, insert special characters indicating locations that have been tried, and eventually become part of the solution path. So we're going to have our position, which is going to be a new position. This is the thing we're going to stick in the stack. We're going to make a deck, which is going to be our stack, but it's going to be a deck. So that's going to be a linked list of positions. So we're going to push our position onto the stack. So basically we're going to use the deck interface for the linked list, right? Because a linked list is implements the deck. It inherits from deck. So we're going to, while not done, while the stack's not empty, so we push the initial position, which is what we're trying right now. We're going to pop it. We're going to try to go forward. If we can go forward, or if we're at the end, then we're done, right? If the maze pos.getX and is equal to the rows minus 1, which would mean we're at the end of the X side, and pos.getY is at the end of the columns, which means we're at the bottom. This would mean if this is true, we're at the bottom right-hand corner, we're going to return done. Otherwise, we're going to push all the different positions that we can try on the stack. We're going to push left, right, or all the way around this, right? There's 4 possible positions we're going to push. We're going to push all those onto the stack as possible positions. And basically that's it. That's what we're going to do. So we're going to do that in a loop. So our stack, we push the initial position into the stack, right? So this is going to be, we're not done because we just started. The stack is not empty because we just pushed something into it. We're going to pop a position. We're going to try this position, which means we're going to mark it as tried. It's not going to be the end. And so we're going to push all these different positions into the stack. And we're going to go back up. So now we've got 4 possible things that we can do. We're going to pop the first one off. The first one off is going to be the last one that we pushed on, which is going to be the one on the bottom. We're going to try that. When we try that one, we're going to push all 4 of them that are around it. And we're just going to keep doing that. So if we look at our push new pos, so the problem that we see here is we're trying to push these positions. These positions may not be valid positions, right? But we're going to handle that. And again, this is kind of an odd design. Personally, I would have like an if is valid pos, blah, 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 push. Otherwise, I wouldn't push. I just feel like the logic for that does not really belong in the push code. It really belongs in the code here, so it's much clearer what you're doing, right? I'm a big proponent of writing code that's easy to read. This code, when I look at it, if you didn't realize what they were going to do in push new pos, you'd look at it and go, well, why are they pushing these invalid positions on here? Why are they pushing positions that have already been tried on here, right? But in fact, you see in push new pos, they're actually going to check and see if it's a valid before they push the position into the stack. So I personally, I think that's bad design, because I feel like this algorithm would be much clearer if we knew that you weren't actually pushing things that were invalid. And then all this thing did, maybe you don't even need this function. Maybe you just straight push, right? But you know, maybe the name of it's bad. Maybe check and push or something like that is what it should be called. But I definitely think that this particular piece of the code is sort of poorly written, in my opinion. All right, so you'll have to think a bit about how this works. Again, what it's going to do is it's going to start. It's going to push the first initial position, which is going to be the top left-handed corner. It's going to push that in. It's going to pop that. It's going to push, because these are going to fail for some of them, it's going to push right and down into the stack, right? Then it's going to pop down or right, one of the two. We have to look at this and figure out which one. I guess it's going to pop right first. Then once it pops right, it's going to push all the possible moves for right into the stack, and it's just going to keep doing that. And if these things are invalid, basically if there's no place, we get to a point, let's go back to our maze here. Let's go back to our maze. So let's say we're at this point here, and we're going to push, well, we're going to try to push up, down, left, right. This has already been traversed, so that's not going to get pushed. Up is going to be invalid. That's not going to get pushed. This is not a valid path. It's not going to get pushed. This is not a valid path. It's not going to get pushed. So nothing is going to get pushed when we reach this point. We're going to go back up to the loop. We're going to pop this one off that we pushed on originally. Or we're going to pop, we're going to pop all the way back to here, because this is the position that this is the only one that's left, right? So we're going to pop back down to this one, and then we're going to keep going with our algorithm. And eventually, this algorithm is going to reach the corner. You're probably going to want to step through this in the debugger to see how this works exactly, to be honest. If I were you, that's what I would do, is step through it in the debugger and see what it looks like. So here's our driver. It's going to make a scanner, enter the name of the file, blah, 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 the usual stuff. Make a new maze. It's going to print it out. Going to make a new maze solver. And then it's either going to say it was successfully traversed or no path was possible. And then it's going to print out what the path was. Well, it's going to print the labyrinth with all the path marked in it is what it's going to do. So that is an example of using a stack for a non-trivial task. We're using it for pathfinding with backtracking. So I guess if you guys have done recursion, you've seen like the Tower of Hanoi problem. There's lots of problems like this where we need to do backtracking. We're doing things for a bit, and then eventually we want to go back. We want to explore a path, and if we can't find the end of it, we're going to go and backtrack. If it's not a valid path, we're going to backtrack to the last branch, and we're going to follow the last branch. So that's it for this. I'm going to flip over, and we're going to talk about implementing stacks using links in the next session. Thanks.